I'm Nitin Dahad, and I'm with Synopsys, Joachim Kunkel, who's responsible for the IP business here at Synopsys. Joachim, hello.
Hi, Nitin.
Well, let's talk a little bit about you're responsible for IP, so let's start at the top. What are you seeing as the general trends in the industry related to what you're doing and what you're seeing with the IP business?
Well, let me look at it the following way. So there's one trend that's been there always, which is everything needs to get faster. Power consumption is not supposed to go up.
Correct.
And that means you need to have, and the number of pins can't go up either, so you need more bandwidth on everything that happens.
Right.
Data goes in and out of the chip faster, gets processed faster on the chip, it needs to get in and out of memory faster.
Correct.
That's just a trend that's called PCI Express Gen 1, Gen 2, 3, 4, 5, 6, 7 pretty soon, right? DDR 3, 4, 5, 6 probably pretty 7, HBM 1, 2, 3. So this is something that's just an ongoing trend that obviously we are absolutely at the forefront of it with our IP business, with our interface IP business. Then there are very interesting things happening in the automotive space. And obviously everybody's talking about this in the area of AI.
Right. And what about security? I mean, that's another key trend.
That is absolutely a trend. People come in different industries, come from different angles. The automotive guys have been very security aware all the time. And the reason is they're very safety aware. And obviously there's no way to provide safety if your car can get hacked. So safety and security has been pretty much two words that have always gone together in the automotive space. And maybe that's one of the reasons that they were among the first adopters of our security IP, together with safety certified IPs. You look at the other area has been the hyperscalers, so the big compute data centers. And what they started to do is they started to secure every single interface in and out of their systems.
At the hardware level.
At the hardware level.
Okay.
And that led to a very interesting development, which was the standardizations of things like IDE as a standard in order to secure things like PCI Express interfaces or CXL interfaces, right? Ethernet historically was always secure with MACsec, right? But then we're seeing things, for instance, in the memory interface. Obviously, it's a very vulnerable interface. All the data makes it in and out. So you would want the data to be encrypted there at that interface, so that when it's in the DRAM, nobody can just tap into the DRAM. So we're doing this with inlay memory encryption. So that actually drove the hardware IP business enormously at the interface security level. The automotive drove it more from a secure enclave, compute enclave point of view.
Yeah. But talking of automotive, and I just imagine somebody was telling me while I was driving in California, everything runs smoothly because the lights, the systems are very good. But V2X, would that help? Because you can imagine if somebody takes over one bit of the system, I'm imagining Die Hard 4, for example.
Security is going to be very important, in particular the part called authentication, which is whatever car is telling other cars that I'm standing or I'm coming or whatever, or I'm next to you, you want to make darn sure that there is ownership of that message, and it's by the driver, right, and not somebody who is sitting 4,000 miles away just having some fun on a computer.
So then you get more complex processing involved, because not only have you got the V2X with the local things telling the car, but also you've got your sensors, your LiDAR, radar, everything. So you've got to now marry that all up, so you need more AI, I guess.
The system complexity is becoming enormous. Right, and it grows exponentially with all the things that we connect to that, and we're connecting things at an incredible rate. Because technically, from a hardware perspective, the only thing that we need to do is we need to connect two things. Our complexity at the hardware level does not increase. Exactly. The complexity increases at the software level, at the system level, where suddenly there's a ×2 in terms of it. So it's a fascinating area. I think the limits are really going to be not what we can build, but what we can afford to manage, right? And what we can afford to power.
We chatted about this earlier. Well, automotive is one of those areas which is driving a lot of what all of us are writing about and talking about, but in conferences. But we shouldn't forget that there's a lot more going on. For example, IoT for a long time, and then the intelligence into systems. and then those things are getting more complex. You've had intelligence, so that's then again a lot more on the other areas as well. So automotive is one area, but there's plenty of others.
Automotive is definitely an area, and it's fascinating how automotive has evolved. I mean, it went from a system that mostly had a bunch of small MCUs, 16-bit at some point in time, 13-bit, 32-bit, but that was really it. I mean, nobody would be talking about automotive as being at the forefront of semiconductor technology as an application.
Right.
That changed radically with the advent of the electrification and also the softwareization, as we like to call it.
Yes.
With autonomous driving, assisted driving, etc., etc. Other really interesting trends also going towards AI is actually on the IoT.
Yes.
Right. So we're having sensors everywhere.
Correct.
Whether it's your air conditioning at home, your heating system at home, your light bulbs at home.
Yeah.
And when you start talking about this, it's not like I have one sensor, you're installing them by the dozens, right?
Yeah.
So the number of devices is just growing exponentially into the billions and billions and billions and billions. And we will want to use those in a more intelligent fashion.
Got it.
And so we're going to start seeing more intelligence basically also at the edge of the IoT network.
Got it. And I think that's what I was getting at, which is a greater intelligence, which is more compute. And then when you apply it to automotive, that's a bigger compute systems. And then that's
Correct.
where we get to, okay, how do we get that performance? And I think one of the areas is, I guess, multi-die, chiplets. Tell us a little bit about those what's happening here.
Yeah, so on the multi-die area, multi-die is mostly a reaction to the fact that we're not able to extract out of Moore's law what we used to extract in the past.
Got it.
We sometimes talk about that Moore's law is not dead, but clearly it's slowed down. So if we still want to be able to cram more functionality onto the things, and we have limits as to how large these chips can get, these dies can get, well, the only option for that, the only solution is just cut it into multiple dies, right? And that comes with a number of advantages. The first one being smaller dies yield much better.
Right.
The other one is smaller dies. Obviously, you're able to extract the heat in an easier way than if you have a huge die, and that's all the mechanisms that you have. Now
and you're also running it higher, everything on higher performance as well.
Absolutely, you can run things with higher performance, right? The other thing you can do now, you can start thinking about combining dies, right? They're all yours and kind of Lego blocks.
Yeah.
You can start combining dies into a package and you have new chips.
Yeah.
Or you start combining dies from multiple sources potentially in the future, and then you have a new chip.
Yeah.
So that changes the dynamics tremendously.
And there's design challenges with multi-die, and in the past, maybe in the 2000s, you had IP blocks came up, and then you could have IP exchanges, and you could then put IP together. You had the connectivity, but now, how do you design for multi-die? I mean, that's part of your raison d'être, isn't it?
Yeah. But let's go back to when IP became what it is, right?
Yeah.
I always say there was a key enabler for that, and it was that we all agreed, well, all relatively speaking, many of us agreed on a particular on-chip bus. Remember, this was the advent of AMBA.
AMBA bus.
AMBA bus, AMBA 2.0, AMBA 3.0 later on with AXI, etc. And with that, we could all build IP building blocks that would connect to something.
That was the idea.
That was the great idea.
Yeah.
So we would agree on the electrical specification, not too difficult, on a single chip, right? And we would agree on the protocol.
Yeah.
And without that, there would be no IP business, or there would be no notion of building SoCs from IP building blocks.
Yeah.
Now map that onto multi-die.
Yeah.
So what do you need? Well, you need to standardize how these things do communicate.
Correct.
And in fact, the industry launched not too long ago a standard called UCIe, Universal Chip Interconnect or Chiplet Interconnect Express. And that's the thing that we believe is going to be providing the electrical specifications so that everything connects, also the protocol specifications so everything connects. Now, you still need to be able to implement that.
Yeah.
And obviously that is a challenge for the whole industry to just make this cookie cutter.
And so how do you as a company, Synopsys, help in enabling that connectivity?
We do a number of things. Among them, we do a lot of EDA tools and we do a lot of IP. And we have a solution that allows our customers to relatively easily put together multi-die systems using our 3DIC compiler, EDA tools, and solution combined with our UCIe IP, or our HBM IP. Let's not forget that HBM is also a multi-die approach to memory. And this is what customers are adopting. This is what we are using ourselves internally when we create all the test chips for our IP, and it's working very, very well.
So UCIe is at a stage where people are using it and implementing it in products.
UCIe is at the stage where it's being designed in and implemented into products. And we're following about, on a regular basis, something like 100, 150 opportunities for chips that customers are actively working on.
And now, I mean, I'm going to use a very funny pun here. Automotive is driving a lot of that business, but tell me a little about multi-die in the automotive industry. So how are you working in that industry? How are customers looking at that?
I think automotive is going at an incredible pace from 8-bit MCU, 1632, to suddenly SoCs, big SoCs that implement assisted driving and autonomous driving functionality. While this is happening, those chips are getting humongous.
Yeah.
And as the functionality continues to grow on these computers on wheels, as they were called once, long time ago, there is exactly the same need. We need to be able to partition that into multiple dies, purely for economic reasons, but also for supply chain reasons, where different companies take ownership of particular functionality into particular dies, and then either a semiconductor vendor puts it all together into a package, or a tier one does that, or an OEM does that. And there's examples across the industry for these different variations of this theme.
I think there's a lot more, vertical integration within automotive companies and tier ones. So they don't all have the capability. So how do you work with them to sort of enable the wider ecosystem to then deliver what they need?
We work with them differently, right?
Okay.
Obviously, there are some companies that are able to make their own chips, right? They have them fabbed, they'll package them, etc., etc., etc. Obviously, what they will need from us would need our tools, would need our IP. Potentially, they would take advantage of some service capability that we have in order to help them get their chips out. On the other end, you have pure semiconductor companies in the automotive space. And well, they need from us the same thing. They want tools, they want IP, they want the IP to be functionally certified for functional safety, providing the reliability criteria, meeting the reliability criteria, etc., etc., etc. And then you end up in the interesting field, which is all the other OEMs. And we have a number of customers who are following the Tesla model.
Yeah.
We're taking it all in-house. We're creating huge chip design departments. And all we want from you, Synopsys, is EDA tools and IP and a little bit of service, right? To others that are asking us to maybe do part of the design for them. Because they say, look, I mean, we have a certain capability, but we don't have enough people to do everything. Could you do a particular subsystem, for instance? And you end up in many cases in interesting situations where you have an OEM taking care of some parts, some aspects, a semiconductor vendor taking care of other aspects, a tier one taking care of other aspects, and ourselves in different roles with the different partners.
Could you see Synopsys providing a broader solution and going sort of beyond the tools?
Well, we definitely go beyond the tools already today with our IP.
Okay.
We are a very broad supplier actually into the automotive semiconductor industry, to call it something.
Yeah.
And we are also providing design services, sometimes creating more than a little subsystem for those companies.
Will there be a limit? I mean, we talk about multi-die. Do you think with current design capability, is there going to be a limit to how much we can build with using multi-dies? I mean, performance is always going to be increasing, or the need for performance is going to be increasing. So maybe not just in automotive, but high-performance computing.
I think the limiting factor is always going to be power.
Okay.
I think obviously the bigger your chip, your multi-die chip becomes, the more complex the problems with the mechanical problems with stress, temperature, etc., become. But at the end of the day, the limiting factor is going to be how much power are we able to bring to that chip, and can we as society allow for that chip to actually consume?
Yeah, because then there'll be the energy shortfall as well, I guess.
We may find an energy shortfall otherwise, I mean, if you just extrapolate the current curves, this is not going to the right direction.
Yes, I've heard that quite a few times over the last year. Let's just finally, sort of what are the key things that you think are important in the whole IP business, and sort of specifically, how do you sort of enable a lot of the high performance compute with multi-die? What's your key sort of takeaway?
The way that we think about this is relatively simplistic. We look at market segments. We look at high performance compute, AI as being one market segment. We look at automotive as being another market segment. We look at the smart, intelligent IoT as being another market segment. And then we analyze the market segments. We look at what IP titles are needed in those market segments. Of course, we also look at what's needed from a tooling perspective. And then it's all about developing all these IP building blocks, the IP portfolio for that market segment, and the right process technology at the right time. And the right time is you got to be the first one to have it. That's the virtuous cycle. You're the first one to have it. The early adopters of the technology work with you. You mature the technology with them. There is silicon proof then relatively quickly, and everybody else is just looking for silicon proven IP. And the rest follows.
Well, Joachim, thank you very much.
It was a pleasure speaking with you, Nitin.